Alright, so we're going to check out this problem. It's going to be amazing. We have a tension in this cable, and this cable here has one tension. Really what's going on here is actually before I start drawing all over the picture, we've actually got two different free body diagrams. So we have the free body diagram that we're going to draw for this guy, and then we can draw a free body diagram for this guy if you want. You can kind of do the two separately. So I'm going to do just the pulley, and the pulley is going to have two tensions on it this way, and then one back this way. So this is going to be this, since it's the same rope, is going to be the same tension, so that's CED. So this is going to be 900 in whatever direction, so I'll just say T1, come on, T1 and T2. Okay, and then whenever I do the boom down here, I'm going to have T2, and then I'm going to have A in all directions. So I'm going to have AX, AY, and AZ. And I'm not preventing any rotations, that's all I have is AX, AY, AZ, and then I'm going to have the force F. Okay, so the geometry here is the thing that's a little creepy. So I'm going to actually move these over here for just a second. Where'd you go? Just like hopped somewhere. Oh well, wasn't that amazing anyway. What I want to do is let's go ahead and look at this straight on for the ZY plane, like this. So what we have is we have the boom coming along here, and then coming toward us and going away from us, we have this set of things that's going on here. Now, something that's important to notice or to think about is that from the side, that's just going to look like a straight line, except it's going to actually touch the boom. That's going to actually look like a straight line with a pulley in the middle, because we're assuming this is a weightless pulley. Like, yeah, in real life it'd be kind of like saggy, like like that, but it's not going to be like that because we're assuming a weightless pulley, because everything is assumed. So from the left, the distance from here to here is going to be 5 feet, and the distance from here to here is going to be 10 feet. So that means that this is a 60-degree, no, that's not right. That's not right at all. So that means we have this angle here, theta. And the tangent of theta is going to be the opposite over the adjacent. So the inverse tangent of, thank you, the inverse tangent of 5/10 is, no, that's not right, thank you, is 26.6 degrees. Okay, so that's 26.6 degrees. So if I'm looking at the boom from this side, that T1 or T2 that we labeled it, that T2 is going straight along here at 26.2 degrees. So I can say that T2, which is what I'm going to call this guy here, T2, is given by nothing. It's given by nothing in the x, and then along the y, it's going to be T2 cosine theta, and that's in the negative direction, and then in the z direction, it's T2 sine 26.6. Okay. So there's that. Now the other forces that are going on here is I have the force F, which I don't know what it is. 0, 0, F. Goes in the negative direction. And then I have my AX, AY, and AZ. So I have A. The support reaction is AX, AY, and AZ. Okay. So let's see. What else can I do with this? Okay. I can take the sum of the moments about A around the x-axis of those forces. F is going to go down. F is going to be like this, and so that's going to be a negative F, which I still don't know, times the distance of 5. All right. Then T2 is going to have one component that goes up, right? That's one component that goes up, and that component's going to be like that. Whee! So that's my sine component, and that's positive. So I have my T2 sine 26.6 degrees, and that distance is again 10 feet away. And then the other component of T2 is right along the boon, so it's not going to cause any rotation of the boon. So I think that's all that I'm really going to be able to deal with. So I'm going to kind of let that slide. So that's going to equal 0. So I have that basically T2 sine 26.6 times 10 equals F 5F. I can't do this for some reason. There we go. 5F. Okay. So I can't do as much as I would like to do with this right now. I don't know what's wrong with me. But I guess I could do the sum of the forces in the x, y, and z. So let's do that. Sum of the forces in the x. I don't know really why I start with the moments. I think my head just stopped working today. That's basically ax equals 0. So that's done. Yay! Then we have the sum of the forces in the y are negative T2 cosine 26.6 plus ay equals 0. And then I have the sum of forces in the z, and that is T2 cosine 26.6 of sine 26.6 minus f equals plus az, sorry. Plus az equals 0. So I've got this one, I know this, I've got this. So these are some equations that will help me do stuff later. Okay. So now I have to deal with the geometry of what's going on with the other two, with the pulley relating T1 to T2. So if I look at this here again and kind of keeping in mind this picture here, so keeping in mind this picture, if I'm looking at E, I need to go R from E to C. Okay, so not entirely excited about this, but I know that this distance from here to here is 8. This distance from here to here is 8, and that's because this one is 2. So I could probably figure out this height. If this is 2, and I know this theta, I could say, oh yeah, I could do that. I could probably also do it with some kind of a proportion thing, but I don't want to think that hard. So we'll call this little part here z. So I can say that the tangent of theta is equal to z over 2. So z is equal to 2 tan theta. So z is equal to whatever 2 tan. I think I just did this, that was done, but that's okay. 2 tangent theta. That should come out to a pretty number, which is 1. Yeah, because it's half. Wait. Yes, it's half. Okay. So that's z. So that means to get from E to C, since I'm already up 1, that means that for the remainder, to get from E to C, I'm going to go from along the x, I have to go back 4. I have to go backwards along the y, I have to go 8. Right? 8 along the y backwards. And then I have to go up 4 more. 6. I'm already 1 up, and I have to get up to 5. So up 4 more. Now, r from e to d is going to be exactly the same, except I'm going to come forward along the x-axis, back along the y, and then up along the z. Okay. So that's pretty. So now I just need to find unit vectors in those directions. So u from e to c is going to be the square root of sum of the squares, which is probably that, but I'll do it anyway. So whatever the square root of 96 is, that's helpful. So something divided by the square root of a 96. So whatever the tension one is, divided by the square root of 96 times this. It's supposed to be 96. And there's probably an easier way to do this. I'm just doing it the way I do it. And then the unit, or the tension, now this is no longer a unit vector, this is the tension from E to C. The tension from E to D is again T1, and it's going to have the same magnitude, except it's going to be positive 4. And then T2, we already have written out up here. So this is like a different system, but that's okay. So this little system here is going to give us the sum of the forces in the x. Oh, we know T1. T1 is given because it says that the maximum that that one can sustain is 900. So these are actual numbers. So that's even better. So for mine, they're 900. Okay. So the x's are going to cancel out because they're zeros, so I don't have to worry about that. But I can do the sum of the forces in the y, and this is like a separate system. That's why I'm making it in blue. So I have, draw my names. So in the y direction, I've got 900 root 96 times -8 plus 900 root 96 times -8 minus T2 cosine 26.6 equals 0. And that's going to give me some kind of an answer, which is good. So I have 900 divided by the square root of 96 times -8 to the... So I have that divided by the cosine of that, and then divided by -1, which should give me 15, 15.7. Just like, yeah, beautiful. Oh, wait a second, wait. I didn't divide. I did that wrong. I was an idiot. I'm gonna try it one more time. 900 divided by, how about that? Divided by the square root of 96 times -8 times 2, and divide by cosine of 26.63. I just like to use exact numbers because then MATLAB Mastering Engineering can't yell at me. Okay, so now I have T2 is equal to 1643. Just like that. Beautiful. Okay, so now that I know T2, I can take that information and go back to my other system equations. So since I know T2, I know that T2 sine 26.6 equals 5f. So f equals T2 sine 26.6 over 5. So I can do that times the sine of 26.6. I should really bring that down. It's not too far away. Divided by 5. And that gives me 146.147. 147. Do that right? Yes. 147. Okay. 147. All right, so that's my force. And then the AY I can also get by plugging that in there. So AY is equal to T2 cosine 26.6. So cosine of basically that times the cosine of come back 26.6. So 1470. I feel like this is off by 10, and I'm not sure how that happened, but maybe it's not. Maybe I'm just crazy. I think I'm losing my mind today. I think I've done too many problems. So I have F, I have AY, I have AX, I have T2. Do I have AZ? No, okay, now I have to find AZ. AZ, well, it's just T2 sine. AZ is F minus T2 sine 26.6, which is that really weird number. It seems a little small, but I guess it's okay. Times T2, which is that, where'd you go? 16 times sine 26.6. And I get negative 588, which kind of sort of makes sense. I feel like I'm doing something dumb, but it's close enough. Anyway, that's basically what we're doing here. I'm happy. I'm happy with this. All right, so there's my answers. Ka-chonk, chonk, and then ka-chonk. So that's really not as bad as it feels like. It's just the annoying geometry to get through. All right, thanks.